So, hello everyone. Today's presentation will be on MaxNovo algorithm. And to start with, I would like to briefly explain what the novo algorithm is. So, in general, the goal of all of the novo algorithms to determine the sequence of peptide directly from a mass spectrum without using sequence database, without using library. Ideally, we would like to get full sequences in this search, but if, let's say, we have a noisy spectrum or missing peaks, incomplete sequence tags are also sufficient. Usually, this algorithm is applied in such applications like S&P monitoring, in discovery of Asian peptides, HLA peptides, generally anywhere where we can construct a database sufficient enough for our needs. And this is, as we probably all know, is how usual HCD or CID fragmentation spectra looks like. It consists of Y and B ions, and that's what most of the novo algorithms are suited for. Note that some amino acids are indistinguishable due to the same mass, for example, isoleucine or leucine. So if you have an experiment when you get different types of spectra, then you probably should still use of library search. So moving to MaxNovo algorithm, it's one of the novo algorithms which is based on constructing spectrum graphs from spectrums. And it's integrated into MaxQuant. It uses a set of predefined scores to analyze the sequences it finds. And it can find both full-length sequences and partial sequences. So moving to the algorithm itself, the first step is pre-processing, and it's the same as for the library search. The algorithm looks for isotope patterns. From isotope patterns, it retrieves the charge state, and then it collapses isotope patterns into monoisotopic peak with charge state 1. After doing so, we represent each peak in the mass spectrum as a node. And the nodes are separated in such a way that the distance between them represents MZ distance between peaks. We also add 4 additional nodes to represent N terminus or C terminus from each side. Note that, so we further construct pathways between these nodes, but we only can construct pathway from the nodes coming from a single ion series, meaning that we don't mix nodes from B ions and Y ions in the same pathway. And the pathway can start either from the left side, from N terminus to C terminus, or from the right side from N terminus to C terminus. So those are examples of possible pathways in a graph like that. And edges between nodes can be constructed if the distance, MZ distance between those nodes, correspond to the mass of a single or 2 amino acids. Why do I allow this 2 amino acid step? It's in those cases, as I mentioned, if we have a noisy fragmentation spectra or we have a missing peak, but we still want to strive for complete identifications, we can make a 2 amino acid step as, for example, you see with this HV step. In those cases, however, we can't distinguish position of those 2 amino acids. And we have less confidence in those edges than with, for example, one amino acid steps. So we can look for, in a recursive search, we construct different paths, complete and incomplete, and then we score those paths, and we choose the best scoring path we have, which will be our best solution. And the main thing, how do we score these pathways? And this is what raw score is for. It consists of different parts, which I'll be explaining now, and the main of them is direct path score. So direct path score is defined as sum of scores defined on edges and nodes of the pathway we're examining. And each node contributes to the score in intensity-dependent manner, meaning that if the node comes from a peak that is prominent and has higher intensity than all the other neighboring peaks, it rewards the score. If otherwise the peak is low and its intensity is lower than its neighboring peaks, then the scorer gets a penalty. Edge contributes dependent on the number of possible edges from the node that this edge comes from. For example, if for this edge we can construct 3 more other possible edges, then we're not so sure about the edge we chose. And this edge will get a penalty. If this is only possible edge from this node, then we're pretty confident that this is the right way to go. This contribution also penalizes 2 amino acid steps, because with 2 amino acid steps you have much more possibilities to go. And finally, path length contribution is dependent on the path lengths, and it rewards longer pathways as we are interested in complete sequences. Next is complement score. And you remember that I said that we only can construct a single pathway from only Y or B series ions, but we're not discard information of another series. In fact, for each pathway, we're looking for complementary ions. And let's say we constructed this pathway from Y ions, and for this node, we see its complementary B ion. And what happens in that case? This complementary B ion or B node will be contributing to the score in the same way, same intensity-dependent manner as nodes in the direct path. Meaning, if it's prominent, it will reward. If it's noisy, it will be penalized. Protease score is pretty straightforward. If termini of the pathway are consistent with the protease we used, then this pathway gets a reward. For pathways that come from B ions, we also check for the presence of A2 ion, as this is one of the most consistent features of B series, and in the presence of A2 ion, we reward the pathway. And if we see water or ammonia loss ions, we also reward the pathway. So in order to assess how MaxNovo performs in identification accuracy, we made a series of benchmarks on the single-shot and fractionated HeLa data. And firstly, we checked how well the raw score is correlated with Andromeda score. And we see a good value of 0.7, which means that raw score, the same as Andromeda, is good in retrieving full evidence from a single MSMS spectrum. Secondly, so there was the task on how to assess accuracy for the novo algorithm. Usually we do precision recall plots, but that's not the case for our settings. So we came up with precision coverage plots. That we defined ground truth as peptides identified by Andromeda, both in single-shot and fractionated runs, with Andromeda score higher than 100. So peptides identified this way were our ground truth. Then precision would be the number of correctly identified sequences by the nova, and by correctly I mean they fully match to the peptides in the ground truth. So number of correctly identified sequences by the nova divided by the number of all identified sequences by the nova. And the coverage would be number of correctly identified sequences by nova divided by the number of all sequences in ground truth. So basically what you see here, first we take a high threshold for a score and we plot precision and coverage for this value. So for high score threshold, we'll have high precision, high amount of correctly identified peptides, and low coverage because there are less peptides that we take. And if we lower the score threshold, we get usually lower precision and higher coverage of peptides that we take. And with this approach, we can actually compare different normalization techniques for our scores. You see, raw score is well defined to retrieve complete evidence from a single spectrum. However, it's not well suited for comparing evidence from two different spectra, which is crucial in getting confident identifications and FDR control. So firstly, you see raw score plotted on this precision coverage plot, and it has overall poor performance. However, with introducing normalized score, which is just raw score divided by precursor mass, the performance goes way up. And then we also made a complete score, which is normalized score only for complete sequences, and the gap score, which shows comparison between first best solution and second best solution for the spectrum. So you remember that we made different pathways in our search, scored them by raw score, and then we have first best solution, and then we have second best solution. And the delta normalized score between those solutions is our gap score. We finally combined gap score and complete score as sum of their two ranks in combined score. And this is the default preferred score in MaxNovo, and this is what we encourage you to use in your experiments when you want to filter your results. With the use of normalized score, we also assessed how different components of the raw score contribute to the search. And in high specificity range, A2 score influences the most results, and in low specificity score, it's actually the complement score that makes the largest contribution. We then compared different algorithms in performance. While novo is overall poorly performs, other two algorithms have similar performance and actually equal area on the precision coverage curve. The difference is that MaxNovo outperforms peaks in high specificity range, and the reverse picture is in low specificity range, as you see here. Then we want to look how well MaxNovo identifies incomplete sequences. And for that, we first of all, we use normalized score because we cannot get combined score for incomplete sequences. And we treated samples of single-shot and fractionated experiments separately. So here you see, for example, single-shot complete with a dashed line, single-shot complete partial, and the same for fractions. And we plotted precision against coverage and precision against normalized score. Here we see that complete and partial sequences identification agree up until the precision of 0.8. And then they diverge, and incomplete have a bit higher precision because it doesn't take those, like, for example, two-step penalties to get the full sequence, and it doesn't strive to get the full sequence, but rather more confident identifications on the short sequence. And with normalized score, we see that complete and short sequences start agreeing after normalized score of 10. And this is, I think, the default. Actually, MaxNovo doesn't have a default threshold for normalized score. It outputs all the identifications, but this is probably the default value that you should choose when you filter your data. Okay, so we also plotted histogram of those partial tags of their masses. And since the y-axis is in log scale, you see that most of the masses are located in this area with medians 250 and 700 for C-term and N-term short sequences. So yeah, most of the short sequences has they do not have overall long length. So I mean, we could expect a complete short sequences, but this is actually not the case in real experiments. We also plotted Andromeda versus de novo sequence length that we get. And even though there are area where they do not agree, and de novo has short attack length than Andromeda, which I explained partially the reasons previously, but most of the values are dominated on this diagonal where Andromeda sequence and de novo sequence actually agree, and this correspond to full length sequences. So then we tested timsTOF Pro data, and firstly observed overall poor performance, and we wanted to know why it is so. And we examined timsTOF Pro MSMS spectra, and what was the case is that this timsTOF Pro spectra have lower, shorter dynamic range, especially in the low mass area. So, for example, for timsTOF Pro, it starts around 200 daltons, and in this area we already see 2 amino acid peaks. So at the start of the sequence, we can make only 2 steps, but not the 1 steps, and we cannot distinguish the position of first 2 amino acids. So if we don't take the position of first 2 amino acids, we actually have performance similar to that of Orbitrap data. And this is shortly how you can set up your de novo sequencing in the run. It's in identification tab, you scroll down and you press de novo sequences. In the settings, you see different, if you want to use different types of scores, for example, amount of rewards for some scores, and this is, for example, a number of steps that you do in your recursive search when you look for different pathways in a graph. And this is MSMS scans table where you can find de novo results. And among the columns that you'll find obviously de novo sequence expression. I say expression because sometimes there are two steps again, and this creates a sequence expression which can be interpreted in many ways, and this is interpreted in de novo all possible sequences. We also have tables with all the types of scores that you can use for analysis, and many more that you can check for yourself in analysis. And thank you for your attention.
So is it possible to combine this with library searches and say I want to do de novo sequencing of everything that Andromeda couldn't identify?
Of course, it's usually goes hand to hand to library search in your run, and you actually have a column if the novo sequence agrees with the Andromeda sequence. So you get both types of results, and you can choose either of them, or you can choose the sequences that are present in both types of the analysis for additional confirmation.